Okay, this is a this is a video on program 25 doing mass-to-mass stoichiometry problems. Given the grams of one substance, find the grams of the other substance, either product or reactant needed or formed in the balanced equation. So before I do this problem, I'm just going to write some steps down. You're like, why am I doing this? You'll see why later. It says find the mass of oxygen. Excuse me, go back to blue. Find the mass of oxygen needed to react with ethane to form 79 grams of CO2. So I'm going to put moles here first. We have 79 grams of carbon dioxide. We need to find the mass of oxygen, so we want to find these grams. That's what we want to find, but the path to do that is through moles in the balanced equation. So I'm going to convert the oxygen and CO2 to grams and moles. I need the molar mass, 32 grams per mole. No matter what the coefficient is, the molar mass of oxygen is the same. CO2 is 44 grams per mole. Water is 18 and ethane is 30. We don't need them in this problem because it didn't say find the mass and product, the mass of every product and reactant. It just says find the mass of oxygen needed to react with ethane, excess ethane, to form 79 grams of CO2. Okay, the way I'm going to work this is with proportions and mole ratios. I will also show the way the internet and other teachers show it with the 4-step unit conversion, and I'll do that later, but right now I'm going to use my method. 79 grams of CO2, we're going to convert that. 1 mole is 44 grams for 1.80 moles. So 1.80. And you may be so tempted to write 1.80 right here for the moles of oxygen, but it is not 1.80. And you may say to yourself, why didn't he balance this equation first? Because I want to do this without the balanced equation. No matter what oxygen is, it is 32 grams per mole. It is not, if it's a different coefficient, it's not 64, it's not 96, whatever it is not anything but 32 grams per mole, no matter what the coefficient is. We don't change the molar mass with the coefficient. It's the same oxygen no matter what. So right now, you're going to balance this. Some of you have already balanced this equation before. That's cool. You have your numbers written down somewhere. For the people who are newbies, pause this video. Beep, beep, beep. Yes, the balanced equation. If you try to 1 here first, it didn't work. So it's going to be 2, 7, 4, 6. You probably started with 1, 2, and 3, and that didn't work, and you could use 3.5. But this is the lowest integral ratios in the balanced equation. So this 4 to 7 ratio, I'm going to do a proportion. 7 over x equals 4 over 1.8. 7 over this equals 4 over this. So cross multiply, x equals 3.14. Wow, that's like pi moles. In my class, every 3 o'clock in almost 15 minutes, 3:14, I always say it's pi o'clock. So we have pi moles here. Awesome. Or 22/7. So now I've got the 3.14 moles because it's almost twice as much. 7 to 4 is almost twice as much. So I'm going to convert the 3.14 moles. Just do a conversion to grams. 32 grams per mole. Over here we divided, over here we multiplied. It's back and forth. And 3.14 times 32 is 100.5 grams of oxygen. What mass of oxygen was needed? 100.5 grams. So I call this a gram-gram conversion, not like your grandma, but like converting grams of something to grams of something else. All right, let's pause this video and I will show the other process of using this 4-step conversion. I'll show that clip later. I'll clip this video and do that. That's a lot of work, isn't it? But if you can see this ratio here, this is a very messy problem. I'll make it cleaner later, but I wanted to see the organic way to solve this. Problem number 1, before I do any balancing and anything else, it says find the mass of hydrochloric acid needed to react with 85 grams of aluminum. So right now, where's hydrochloric acid? Yes, it's right here. So we want to find first the moles, but then we'll find the grams. Okay, for the aluminum, I'm going to use my mole ratios right under my balance equation. So I'm going to put moles there. Why didn't I put the mass there? Because you can see the mole ratios very easily. 85 grams of aluminum. So we're going to go to the moles of aluminum, use their mole ratio, and go from the moles back to the grams. So I don't need the molar mass of these two, but I need the molar mass of aluminum, which is 26.98 grams per mole, no matter what the balance equation is. And HCl, hydrochloric acid, is 36.45 grams per mole. Now pause and balance this. Beep, beep, beep. Yes, you probably started with a 3 here, and then a 1, 1, 1.5, but I'm going to use the lowest ratio of integers, 6, 2, 2, 3. And there we go. So basically, hydrochloric acid is going to need 3 times the number of moles. When I convert the aluminum, 85 grams, I'll edit this out. I'm going to put the 85 over here. 85 grams divided by 26.98, and I get 3.5. Wow, almost pi. Wow, that's pretty cool. I did not plan this. These are random problems. 3.15, sorry, 3.15. It's going to be 3 times as much. So some of you can see in your head, multiply this by 3, but I'm going to use a conversion. 6 over x equals 2 over 3.15. 6 times this divided by 2. In other words, it's 3 times as much. It's going to be 9.45 moles of hydrochloric. Then we're going to convert that 9.45 moles of hydrochloric acid times 36.45 grams over 1 mole. Moles cancel. And 9 times that is 344.5 grams. Now, this is a theoretical example. You don't go in the lab and say, I'm going to find 344.5 grams of pure hydrochloric acid, because hydrochloric acid is by definition, it's an acid, it's dissolved in water. So what you'd really do is find the number of moles per liter, which is molarity. And some of you have seen molarity before, but most of you, if you're learning stoichiometry, you'll learn about solutions later. So instead of we'll learn what volume we need, how many millimoles and milliliters of this. You'd find a concentration of hydrochloric and find its volume is what you'd really do. But technically, you would need 344.5 grams of the HCl species to react with 85 grams of aluminum in this problem. And you'd find the number of moles and grams formed. So 85 plus 344.5 is like 400 something. So these two would add up to the sum of these two by the conservation of mass. And if you watched my previous video, you saw me find all the massive products, the massive reactants, and the mass is equal before and after. 2, 3 significant figures if you're careful on your rounding. Very good. This is a very organic way, and I will show the nice, tidy solution in a moment. Okay, here's our methane combustion. So beep, beep, beep. There's problem number 1. Problem number 2, beep, beep, beep. And problem number 3, beep, beep, beep. I didn't do a hard balancing on all these. These are very simple. Maybe 1, 2, 3, 4 on the coefficients, not anything large for these simple problems. And later, for some of you, when you get there, you'll balance octane combustions, or you already have maybe. And there'll be big coefficients here. I believe it's 2, 16, 18, 25, if I remember right. It's a very large coefficient. So this is the stuff in your gas tank. It's octane. All right. So good luck on these other 3 problems. And the people at home, people in class, yeah, we're going to have some fun on this one. Why? Because you got to do 1, 2, 3, 4 things in a row right, which for some of you teenagers, it's not going to happen the first time. Some of you, it will never happen. You'll always flip around and just miss something. But a lot of you will get this if you're diligent and careful, and if you my work is sloppy, isn't it? This is not very neat compared to my other videos. I will show the neat, tidy one in a moment, but this is very organic. This is how you do it. This is how we do it. Okay, good luck on those next 3 problems, and I will definitely have interactions with most of you on these problems. Okay, this is one of the tougher things we've done so far. Good luck.